All right, so change of gears today. I'm going to start talking about consistency and replication. And since we only have 1 hour, I want to first give a very broad overview of where is this going, what's the kind of stuff we want to do in there. And also to paint some sort of a more realistic picture of what you should expect. Right? So now one of the things I've been saying for all the class is you're mostly talking about compromises when it comes to solutions, and there is no such thing as a perfect solution. It turns out that for consistency and replication, that's taken to almost an extreme. You might have some sort of a shred of a class of reasonably good solution in the other ones, but for this one, you gain on some and potentially lose massively on another part. Right? So when it comes to consistency and replication, replication is not going to be so bad in terms of what does it do, but consistency is going to be something that's truly awful in a fundamental way. Okay? On portions, we can kind of resolve the thing, but there is almost no good solution. If you want to have a solution that gets close to some kind of very nice semantic in terms of what it guarantees, it's disastrously inefficient, right? So things get pushed really to an extreme when it comes to especially consistency. Now, replication, depending on how tight it is connected to consistency, can be anywhere from yeah, no big deal, let's just do it, to oops, it's about as hard as consistency. Okay? So I will talk first about replication because it's easier to talk about the replication, but keep on pointing out that if you want this property to hold, you're in the land of consistency. Okay? Let me say a few words about consistency first. Okay, so the trouble with consistency, I mean the first problem with consistency, is in fact the definition. Okay? It's the fact that it's very hard to come up with an actual definition that we are really, really, really sure that that's the definition of consistency. And I want you to understand this. I explain a lot more in a database class about this thing, right? And I want you to understand from the beginning, you can write a million papers about consistency, but ultimately, all of them are built on top of something, and that something might be very shaky to define. Okay? So I'll go into some details to explain what that means. Okay? So, I mean, consistency is related to the notion of correctness. Because if you don't have a notion of correctness, it makes no sense to say, I maintain some correctness. Consistency, it's about maintaining some sort of correctness when you go and you do distributed systems versus something else. But the trouble in the first place is the notion of correctness, right? So I can define consistency with respect to correctness, but then how do I define correctness? So let's take an example, for example. I mean, just to start with. You write a program. I ask you to do a task. You write a program. How do I know your program is correct? I mean, who says your program is correct? By the way, judging by the number of defects, bugs, whatever, in software in general, even when everybody is convinced something is correct, you still discover that something is not correct because of bizarre things, right? So correctness of programs, I want you to understand correctness of programs is really into the fabric of the notion of consistency, and that in itself turns out to be extremely tricky. I mean, really, really tricky. By the way, we do have an idea how to tackle correctness of programs. It's only devastatingly bad for the programmer, right? So you can actually write programs that are provably correct. But to do so, I mean, let's see. This is kind of a complete shoot in the dark. Right. How many of you heard ever about proof-carrying code? Proof-carrying code is a piece of software that you wrote that contains annotations that prove that the program is correct. Right? To prove that the program is correct, you have to prove that it produces the right output given the right input and it cannot run amok. I mean, you get into subtle things like you never access memory you're not supposed to access. How would you prove that? How would you do these kind of things? In languages, right, people spend a large amount of effort in trying to nail this down. Okay? And they did come up with some mechanisms to do so. But again, you can write programs that are 10 lines long for which you can prove they are correct. When I was a PhD student at Cornell, for example, we got one of those, right? So those guys were crazy about proof-carrying code and the notion of correctness. So in the qualifying exams for the PhD, they threw a problem in, right? And they said, write this program and prove it's correct. I spent a good part of half an hour to write 5 lines of code and then to prove the 5 lines of code were correct. Good luck in doing that on an industrial scale when you're doing code design, right? So keep this in mind. And this is kind of the ultimate way to say, yeah, forget about whatever super strong type of consistency. You don't even know if your program is correct. So the traditional way to go around this problem in the first place is to hang on to some notion of correctness that's more likely to be correct than another notion of correctness. Namely, you say, let's assume that the sequential version of the program is correct, right? Let's now define correctness for distributed versions, multi-threaded or multi-computer or whatever, with respect to the correctness of the sequential one. Now, by the way, this is the attitude and the approach taken in the database literature. And database people are the first ones that actually looked at this notion of consistency. It doesn't matter what the distributed systems people are talking about, right? Why? Because banks were extremely interested in relational databases, and they are extremely concerned about some sort of guarantees that the distributed version of the program, the multi-threaded, anything you want, doesn't run amok. But again, it's with respect to that sequential correctness, right? So one way to define consistency, and I'm going to come back to this later, is to say, whatever you do, make sure in some sense is equivalent to the sequential program, okay? But of course, you might have multiple such sequential programs running, right? And in principle, you have to overlap the execution of such sequential programs. So when you define consistency, you have to say not only that's equivalent to the sequential execution, but it's also equivalent to a sequential execution of the sequential programs. So you take your sequential programs, you shuffle them in some order, and you run them one by one. Now, nobody says you should run it like this, but one way to define consistency would be make sure that you're consistent with at least one of these possible orders. Okay? So what I'm trying to say is, when consistency is involved, you have extremely complex issues popping up, and they cannot be resolved completely. Okay? Now, throughout these lectures, especially on Tuesday, I'm going to talk about all kinds of notions of consistency that were introduced, especially in the distributed systems literature. All of them are iffy. Okay? All of them are highly problematic. There's no such thing as completely clean ones. Database people nailed it down a little bit better because they have a connection with this kind of a notion of sequential consistency. But of course, distributed systems people said, hey, that's a solved problem in databases, which it is. Let's invent other kind of problems, and let's try to solve those as well. Okay, so I'll plow through all of these things, at least at the high level. Let's go back and focus on replication, because this is a lot easier to understand. What does it do, and what is it supposed to do, and so on. And sometimes replication is easy. Okay, so when it comes to, replication is basically what the name suggests. Let's take the data and put it in multiple places. Now, of course, the question is why? I'm sure there is a slide here, but let's forget about the slide. Okay, let's just brainstorm about this. Why would I replicate the data? Let's throw reasons out in there, right? One of them is have multiple copies in case you lose some. Okay, so this is some sort of a backup, right? So one reason to do replication is to have a backup copy. That's a very legitimate reason. Now, what's the difficulty to doing this kind of backups? What could be the difficulty? Yeah, so one is headaches, remembering where your backup copies are, let's say. Okay, so that's one issue. I'm sorry? Well, inconsistent data, first of all, what does inconsistent mean? And this is very, very tricky. Right? But if I do it for the purpose of backup, I might not care that they are in sync. Or, well, so the question is, when do I fire up the replication process? Right? So when do I create a copy? So if I want a replication for the purpose of backup, the question is, when do I propagate changes? Right? So replication without changes is truly easy. If you have a very slow changing resource of any kind, replication, it's a walk in the park. You just, whatever, do it. Okay? If you have an extremely fast changing resource, replication becomes a nightmare. For example, imagine a database that processes hundreds of thousands of transactions per second. And we have those databases, by the way. For example, Visa has them. Now, clearly, all those transactions, you have to remember what they were, how they did, and how they changed the state of the system. So replication there is much, much, much harder than you backing up, I don't know, your term papers or whatnot, for example. Right? Again, it depends on how fast let's say the primary copy is changing. Okay? So again, this is why I'm saying that replication could be easy or could be extremely hard. For example, how do you think they do replication in that database? They literally have to probably remember the sequence of actions to be able to apply them again, right? And it's very tricky, but the database community did deal with that, right? Techniques like, for example, the logs, in which you simply write what is it that you are doing. So you don't have a copy per se. You have a sequence of actions that will produce a copy should you need one. So what a copy means and what you replicate, it's kind of in the eye of the designer, not necessarily the beholder. So you don't necessarily need a copy. You don't need to say stop and copy. You can have anything that could lead with further processing to a copy. Now, a fundamental question about the replication is, how often will you go and use the replica to do something? Okay, so when it comes to backups, the answer is almost never, right? Most of the time, you don't care that the copy even exists. Only when, by mistake, you delete your files and you do something, you go and recover from the backups. For example, I don't remember ever going back to a backup and doing something, but hey, you still need to do the backups because you're going to run in trouble sooner or later, supposedly, okay? All right, so that's one reason to do replication, not to lose information. And then the main question is, how often do you replicate? Because whatever you did not replicate, you're going to lose in case of some sort of failure, right? So when it comes to backups, common practice is to replicate every day, for example. Of course, if it changed. If it didn't change, again, you're out of the woods, you're fine. What's another reason to replicate? Yes?
Like you have two replicas in different areas, and the person who's closer to the one replica will access that one.
Right, so performance. So another reason to replicate is performance, and this is exactly what Akamai is doing. Right? So you pay a lot of money as a company to Akamai because they have really clever replication algorithms, and they are, in some sense, geographical replication algorithms under the assumption that, of course, I'm going to access a closer resource faster than a faraway resource. And keep in mind that one of the big problems and big enemies in distributed systems is latency. You see, we can deal with a lot of other problems. Right? For example, if you don't have enough bandwidth, we know how to increase the bandwidth. We put more money into it and we increase the bandwidth. Okay? This is why the internet gets more and more bandwidth, but the internet doesn't get lower and lower latency. Right? So latency, it's a physical limit. We don't know how to go beyond. I mean, one way, so let's say we maxed out how much information we can send through one optic fiber, which we haven't yet, by the way. And some people compute the limit to be something like 40,000 times larger than it's actually accomplished now. So let's say we even max that out. Hey, you put more cables through the ocean and you get more bandwidth. But that's not the case for latency, right? So PBS yesterday had a documentary about speed, and part of the speed was internet speed. Right? I gave you the example with they want to put between London and New York that cable for the ocean that's straighter. Okay, so I've heard another crazy idea yesterday in the documentary, and this is all about shaving a little bit of latency, right? So apparently a company, and it kind of failed, wanted to put a straighter fiber between Chicago and New York. Why? Because you have companies trading on both the Chicago Stock Exchange and the New York Stock Exchange. Whenever you have the same thing happening in two places, whoever gets the information across that something changed will win, will make money. These guys make money on fractions of a penny just because they do a tremendous number of transactions. Okay? So it's a game of fractions of pennies, but just doing many of those, right? So they were interviewing these guys that are basically responsible for 1% of all the trades on New York Stock Exchange or something like that, right? And they're all kind of just babysitting those millisecond trading machines. And in that, and they were talking about the fact that one of the companies were trying to put a straighter fiber, but they had significant trouble because they had to go through people's properties. Then they tried to make an almost straight fiber, and they were shaving off 1 millisecond, 1.4 milliseconds. They were talking about saving 1.4 milliseconds in latency between Chicago and New York. And then this guy said, hey, we have a secret weapon. We figured out something that's more interesting. And it turns out, according to them, that the secret is to use microwave technology to send the signals through air rather than send them through the optic fiber. Because, and this is why it's important to know physics, the speed of light is higher through air than it is through glass. And they can shave off more than that 1 millisecond by sending things through microwave towers. Okay? At least they hope. Okay? Now, of course, they have to put their servers next to the microwave towers to make sure that there is absolutely no delay to get to the microwave tower, which is next in the other place, right? So it can actually get quite crazy. Okay? So keep this in mind. I mean, this is going to be a fight that's going to go on forever until somebody figures out how to do some sort of instantaneous communication. Okay? Latency cannot be reduced. So when it comes to replicas, that becomes very either advantageous. You could do replication to mask latency. And it's exactly what was mentioned before. And this is precisely what Akamai does. Internet is a big world. It takes, I mean, to cross the internet, to go US to Australia, you're already talking about hundreds of milliseconds, okay, no matter what. Even if you're in the financial markets and so on, right? I think the latency through the fiber, even through a straight fiber, New York to Tokyo, it's about 170 milliseconds. Okay, that's it. You can't go below that. I mean, you can do computations if you want, in which you put the speed of light. It's about, I think, about 60% of the speed of light through the glass. Now, of course, a problem with sending it through air is what? You must have a straight line. It just happens that the Earth is curved. If you actually, you can do this, and you can do this with radio waves. You can bounce it off the ionosphere, right, or some other parts of the atmosphere. But that makes the path even longer, so you're worse than the fiber. It's weird. It's a physicist's world suddenly, right? Okay, nevertheless, so you have a large internet, and to cross it, it can take 200 milliseconds easily. But if you do replication, by the way, do you know how fast you can access, for example, a computer in the department? Oh, you can tell, right? The ping program does exactly that. So what does ping do? It sends a special packet, and the network card that receives the packet immediately replies. Ping was introduced precisely in order to estimate latencies, right? And this is how you know it's good when you get latencies well below a millisecond, right? So if you ping a machine in the department, if you have a decent connection, you're going to get 0.5 milliseconds. You ping yahoo.com, you're going to get 80 milliseconds. I don't even know where Yahoo is, right? You ping something in Australia or something in Japan, it's going to be 200-something milliseconds. You can even try it, right? If you have a Linux machine. It's possible to do it from Windows, but it's more elaborate, apparently, right? So by placing replicas close by, you can get within that 1 to 2 milliseconds rather than 200 milliseconds. 200 milliseconds can be devastating, for example, for user experience, right? So also, that's an indication of to what level you should be paranoid. So I want you to remember these numbers because they turn out to be very important, right? So arguably, humans cannot perceive anything that's below 30 milliseconds. This is equivalent to roughly 30 frames per second, 30, 35 frames per second. Now, some people claim that they feel better when they play video games at 60 frames per second. Some people brag about their TVs that can do 120 frames per second. None of that matters when it comes to the refresh rate for the brain. I mean, simply the visual system of humans cannot run faster than something like 30 milliseconds. Whatever, by the way, that's one of the key ingredients in any magic show. The hand can move faster than 30 milliseconds. You can move your hand, if you're good, you can move your hand from here to here and back faster than 30 milliseconds, right? Or definitely from here to here faster than 30 milliseconds. That means the visual system cannot get the movement, right? So magicians are very fast movers in the end, and they also know how to distract you, right? So beyond a certain point is now we're sweating it below, for example, 30 milliseconds, no matter what people are telling you, right? But 200 milliseconds is devastating because you can actually see and you suffer through why do I have that delay? People really hate delays, right? So even if you're tackling a simple problem, which shows up almost all the time, right? And trust me here, this becomes very, very important, right? So you have a nice interface and, for example, a nice visual system to look at stocks, let's say. And people really want to look at all kinds of pretty pictures with stocks, graphs, and whatnot, okay? If you have to communicate with the backend server and come back, unless you have a server that's placed very, very close to the user, this large latency will hit you, and the large latency is going to be very annoying in the user interface. One technique is to move the data that the user pulls off in order to display whatever it's on the screen, or whatever the user pulls off, closer and closer and closer to the user, okay? So this is, as I mentioned way before, that this is what Akamai does. So for example, CNN, so I know for sure it's a customer of Akamai. CNN basically pushes whatever changes to the content they have through the Akamai system, and Akamai will very, very fast and efficiently through the network distribute it much closer to you. and there is some hijacking that goes on at your ISP. When you say www.cnn.com, you're not really going to whatever CNN is. You're going to go to your local replica. So replication does need some collaboration or support, either from the client or from the infrastructure. It's not possible to do replication without somehow diverting things to different replicas. Okay? So one core issue with replication is how are you going to divert things in case they fail? That can be done as easily as, for example, this is the core idea behind mirrors. You first try the primary replica, and if it fails, you try the second one. If it fails, you try the third one. Of course, it's very annoying because it can take a long time to go through the replicas, wait for them to fail and whatnot. With replicas, you could do load balancing. So ignore the fact that they might be close to you or not. If you send people to one of the many replicas, essentially you're reducing the load on a single replica, and you're spreading the load. And this is the notion of load balancing, right? So replicas are crucially related to replica. Load balancing reduce latency. Right? So what other things can we do with replicas? Yes? What's the difference between a primary server and a replica? Oh, mirroring. Well, so let me mention something. People in general like to invent new terms, even if they are very close to old terms, because it looks better, cooler, newer. For example, cloud computing is one of those, right? It's only 50 years old now, right? The first ideas behind cloud computing were introduced easily about 50 years ago. The moment they had two computers, they wanted to create some sort of a connection between them, okay, and to do something, except that now it's super cool, and most of the technology behind cloud computing was invented a long time back, right? So this is the rule of thumb that I apply. Every large area in computer science or technology, every decade is going to pick another name for something they've been doing for a long while to make it look fresher. Okay? Yeah. Condor system, for example, was developed in the 1980s, and it did almost anything that modern cloud computing stuff does. It's just more excitement. It's the same thing here. What's the difference? Not much of a difference. The problem in general, and this is what I want you to remember, the problem in general in distributed systems, but a lot of other things, is people don't really take the time to really produce a definition. They say, oh, replication sounds cool. You say everybody who's supposed to know about replication should know what replication is. Hey, it's English, right? What's replication? Let's look in the dictionary. Well, the dictionary is not going to say, yeah, look in the dictionary and see the difference between mirroring and replication, right? So what I'm trying to say is people don't take the trouble to define things. Then words morph in meaning. What do they mean and they don't mean? And ultimately, a lot of things are very close to each other. So to some extent, you can think about this kind of replication as some sort of caching. And for example, you can ask the question, how is this different? How is replication different than caching, than different than mirroring, than different than something else? Well, in substance, they are not different. They are the same kind of thing. You might produce some refinements which probably are going to be broken by the next guy that comes and does some replication service just because he thought the name is cooler, right? Let's call this replication, though it's not quite replication or things like that. So don't put too much in the name, right? I would say, in essence, nothing between mirroring and replication, right? Now, specific guarantees that a specific service offers, that's a different story. So traditionally, mirroring services offer very few guarantees. For example, they never said the copy is fresh. And for example, some of the mirrors of the important software, like the Linux kernel, are notorious for being back a couple of months. Right? So if you use that mirror, you're going to get a version that's a couple of months old. That's not too good. Akamai is famous for having replica propagation in seconds at most. Right? So it's not so much what's the difference between the terms, is what's the difference between specific services offered by specific tools, companies, or whatnot. Okay? So to a large extent, the replicas are related to caching. And remember, caching is a fundamental technique in general. And what does caching do in general, right? It allows me a faster access to that resource at the expense of having it not quite in sync with the rest. But that's essentially what replication potentially is. Right? Now, one thing that we are going to see when we talk about various kinds of consistency is you could insist that the replicas are completely up to date. But that's going to be really burdensome on the framework. right? So again, you can't really say, I mean, you can basically, for example, this is one kind of very harsh consistency you can impose on replicas, is you activate the replica only when you're sure that the changes were propagated to all other replicas. So that to any user, no matter where they connect, right, it looks like we all switched to the new version at the same time. Right? So you have changes, but you don't make, for example, the changes available until everybody got the changes. And this is equivalent, for example, and this is done sometimes in databases, when you have these distributed transactions, which is, we still have to talk about. So you want to make sure, for example, that you say commit to a particular transaction to the user. You tell the user, yes, your transaction actually finished correctly. Only when all the parties involved agreed that we commit to that transaction. And this is extremely harsh. The moment you use such a mechanism, be prepared to pay a very high price. Okay. Large number of message exchanges pay a large amount of time because of the latency. Forget about any other issue. Okay. So we do replication not to lose data. We do replication to reduce the latency. What are the reasons? So for example, how would you do this, right? So I'm talking about this 30 milliseconds here. I want to update graphs. I want to do this kind of thing, right? So what Akamai does is nice and good. Potentially you could do better if you can compress the data a lot and the data doesn't change so much, or at least can be considered stationary for a few minutes. But you can actually, instead of having the web page generated in a server, you can generate it in a client. And this is something you're not really told. I mean, this is the new brave new world in which you just ship the data to the browser, and the browser will create all of that, all of those pages. Now, this is JavaScript magic, right? If you do so, you can do some amazing stunts that are not possible otherwise, right? So for example, a particular problem that a number of data visualization companies have is they rely on backend servers, which means they need this, it's not 200 milliseconds, by the way. It's much closer to 1 or 2 seconds. The moment you involve database servers and all kinds of other processing, if you say, give me the graph that shows me the stock for this company over the last 5 years, right? Your browser talks to the web server, who talks to the backend, the database, which computes the new graph. You push it through some sort of a, compute some sort of a feature or whatever, ship it to the front end. If you don't believe me, you can use these tools. It feels like a long second. A second wait is devastating for the human brain. It really makes you feel bad, right? It bogs you down. You cannot think, especially if you expect to go through hundreds, thousands of these things to see anything, right? Faster than 30 milliseconds doesn't matter either. That's the trick, right? So staying close to 30 milliseconds makes it look like a movie, right? So think about it. You would like to find an interesting stock, and by the way, your brain can easily run at 30 milliseconds a frame. And you can actually see patterns at 30 frames per second. Right? Not only that, but the human brain is really designed to see patterns in moving things, not in static things. If I give you a static picture, you're going to have a hard time figuring out what changed or what didn't change. If I give you a movie, you instantly know what's important and what's not important, right? So from that point of view, you're better off essentially producing some sort of replication of the data in the browser. So suddenly replica has a different meaning, right? So now, for example, is that a good investment or not? To push the replica in the web browser. Well, one of the tricks that almost always is a good trade-off in modern distributed systems is to trade off throughput for latency. So how can you do that? Well, so that means do a lot more replication than otherwise you would think. When the user, for example, starts to look at stocks, right, you have to pay, for example, 200 milliseconds, or you have to pay, for example, a second, right, to access a single picture, 1 second. You can ask yourself the question, if the user is willing to pay 1 second, or maybe even, let's say, 10 times more, but not to pay any price afterwards, right, namely stay within 30 milliseconds, how much could I ship in 2 seconds? So ask yourself the question, with modern networks, how much information could I ship to the user in let's say, 2 seconds? Because the trick I can play is the following. Instead of doing everything piece by piece, if I have some idea in what space the user is going to stay, at the first request, instead of shipping only the little thing that the user wants, I'm going to ship 2 seconds worth of information at the bandwidth that the user has. Right? Now, if you have a decent internet connection, that bandwidth, right, you can buy this, for example, in certain parts of games, but now that bandwidth could be as high as 1 megabyte per second. Okay? So 2 seconds is 2 megabytes. In 2 megabytes, you can easily put quite a lot of information for all the 10,000 tickers on the stock market. So what I'm trying to say there is, when you design distributed systems, think about replication as something that's really your friend and bring it possibly even much, much closer to the user. So one way to do it would be to really ship almost all the information to the user, because then the latency is below the radar of what the user can actually perceive. You have no latency to go to the back. Now, sometimes this strategy works very, very nicely because the data simply doesn't change that much. Right? So for example, if the stock data, so if the user wants to look at historical data, for example, what happened at the granularity of 1 day on the stock market, spending 2, 3, 4, or even 10 seconds to ship the whole history of all the stocks that within some kind of a range for the user. For example, you don't have that many stocks, actually, about 10,000 of them, right? It's not something that you should dismiss. Once you've done so, if you have the horsepower in JavaScript to really generate all those things that normally you would get from the backend, you have completely seamless execution of this, right? So an example of this, for example, is what we try to do with this Medicare data. It takes about 2 or 3 seconds to ship 163,000 rows to the JavaScript. After that, it's all below 30 milliseconds, and you feel like there is no effort whatsoever, right? So that's really a form of replication. I replicated the backend data. Right? I took care to compress it a little bit and make it smaller and so on. So all kinds of tricks to make it as small as possible. But once I ship it to the front, you have a replica in your browser. In the case of the Medicare data, for example, we know for sure that there is no updates to it. The feds have no intention to give more of that data. Right? It did not change a single bit in 4 months. And it's not clear at all when it will change. The same thing with the stock market. It won't change at the resolution of more than once a day. Right? Because I'm only providing you the low-level service, which is the average price per day, right? So in those kind of circumstances, really the replication happens very, very close to the client. You can think of it as some sort of caching, but it's in fact some sort of replication, okay? It's kind of blurred anyway, right? Now, when it comes to these fast transactions, fast changes, things become much, much, much harder. Right? So for example, if the user would really be interested in very up-to-date information, then how do you provide that? How do you provide that replica? So one thing, and this is related to some deep questions about operating systems, right? I might as well connect them. So a lot of these problems are really problems even if you don't have distributed systems at all, and I'm going to explain in a second, right? So imagine now you're tapping into all the activity that goes on any market in the world, okay? It turns out you can buy such a service, and there are for example, there's a company called Nanex. And this company provides an extremely fast data stream that gives you access to all the transactions that happen on all the financial markets. Okay? Now, you pay an arm and a leg for that data stream. Don't get me wrong. But to some people, it's worth it, because that's how you find out about activity on all the markets. And that data stream itself is 40 million transactions per second. Right? By the way, to even ship that many per second, they have to have a very fixed format. So they have something like a 64-byte. So they have 64-byte packets. So we are talking about things that suddenly, instead of being very, very high level in the application and being some kind of a fluffy thing, they get pushed all the way to the bottom. And they are this really tight, specified in C format, 64 bytes, to specify each of the transactions, 40 million transactions per second. So they say, hey, if you have a fast enough internet connection, no problem, and you pay the money for the service, we'll stream to you the data. In fact, what they are doing is they allow you to replicate everything that happens on the financial markets. Right? That's similar to the kind of stream that Akamai might send to their servers to propagate information. So that's an implicit specification of the replica, not an explicit one. But you almost always have to do this. So let's think a little bit about some form of replication that you might not even think they are replication, but they're really replication, and which are core operating system issues, have nothing to do with distributed systems. Okay? So here is a similar problem, even though usually people don't paint it as a similar problem. You have a program, and it runs for a while. A while being, let's say, a couple of weeks. We have those running in the department, by the way. Large simulation or whatnot. Okay? Now, a big problem with those programs is if the program for any reason crashes in the middle, for example, power outage or any other reason, programming error or the wind blows too hard or whatever, right? You lost many weeks. I know physicists that were running their code for months Good. So one interesting idea there would be what? Why don't I replicate the state of the program at certain points? It's called checkpointing. So that if the system fails, I can only go back to the checkpoint and continue from there, saving that. I might lose, for example, a minute. Let's say, if I checkpoint every minute, which means if I produce a replica in another form on a persistent storage, then I can go back and lose a minute and pick up the computation. No big deal. Okay? So then the fundamental question is, and this is a problem that looks like has nothing to do with the rest of them, is, OK, you have your own favorite sequential program, no strings attached with distributed systems. You need to provide checkpointing for your program, just because it runs too long. Now, supposedly your program doesn't just execute infinite loops. It does some changes to the state. How do you replicate? How do you replicate the in-memory state to some sort of a disk state? Because that's persistent. So how do you do it? This is, in fact, a core replica issue. You almost have the full-fledged replication issues right there in that problem. Now, this is something people looked at for a very long time. And they don't necessarily have a very good solution. What's the core problem there? Which is very similar to the core problem in distributed systems. The core problem is you cannot really use the easy way out. So what's the easy way out in that circumstance? Freeze the program, take a full dump of the memory, and put it on the disk. Right? Now, this is provably a good solution. The full memory, so if I dump the full memory state and the state of the registers, I capture the full state of the processor. Well, Intel guarantees that this is the case. So that if I fail, I can just recover the full state of the memory, recover the full state of the registers, and say, yeah, continue from this point, and it continues. Right? Now, this solution has a major advantage. And the major advantage is it does not depend on any semantic related to what the code was doing. Okay? It's truly a universal solution. I don't care what you do. This is, in fact, a provably good and usable replica. You're only going to lose the amount of time you lost since the last replica, because that's guaranteed by Intel, who says our computers behave deterministically. By the way, something similar is used, for example, when you use this virtualization technology, right? And you say safe state of the virtual machine. That's, by the way, one of the tremendous benefits of the virtual machines. You can freeze them, right, and later come back to them, or move them on a completely different machine and come back to them. They really save the state, and you can continue running the state. So for virtual machines, this kind of checkpointing, it's in fact trivial if you're not particularly concerned about the performance of this, right? Just save the state. I mean, you have to stop the program. Why do you have to stop the program?
State's changing.
That's the trouble, right? So if you have a regime in which the state is changing and you're trying to do this checkpointing, the problem suddenly becomes much, much, much harder, potentially. And it's similar to the conflicts you get if you don't use mutual exclusion regions. You don't quite know what you get when you saved it. You see, the problem is not saving something. The problem is how the saved thing or how the propagated thing to another replica can be used to recover something that's some sort of a consistent state. So you see how consistency comes into play, right? If I freeze the program, remember all the registers, and dump all the memory, I have a reasonably good ground to say I get a consistent copy for that moment in time. But almost anything off that, it's plagued with problems. How do you know that you didn't get something that's a mess up, right? So almost anything except this very, if you want, barbaric solution, right, would require very, very fine-grained considerations with respect to what is it that the application was doing, and proves that a particular replication strategy, a particular checkpointing strategy, is kind of the same in this circumstance, does not mess things up, produces a certain level of consistency, right? Now, I just want to point out that in the context, a very restricted context of relational databases, the database community spent an enormous amount of time figuring out exactly what this would mean, right? And they came up with this kind of algorithms, a large number of them providing a certain kind of consistency, right? So for example, an interesting idea would be, can you checkpoint as other things are going? And it's possible to do in restricted domains like the databases, but they needed 20, 30 years of research to nail down the solutions. In general, there is no universal solution, especially if you expect very fast kind of replication process, right? Another way you could try to capture this, and this is potentially something interesting, right, is you say, hey, The state is enormous. By the way, size of the state is a really big problem. For example, you can buy now 128 gigs of memory with about $1,000. It takes a tremendous amount of time to save 128 gigs of memory anywhere, to push it anywhere, right? I mean, even if you talk about extremely fast disks, extremely fast disk arrays can achieve 2 gigabytes per second, let's say. Let's say 4, let's be generous. Okay, 4 gigabytes per second, 128 gigabytes, right? But if I have 4 gigabytes per second, I need tens of hard drives, right? Then let's bring it up to something like 512. 512 gigabytes, and this is, by the way, doable now on a single machine, divided by 4 gigabytes, and we are talking about 1,028 seconds, right? It's a disaster. If I really want to capture the full state and replicate the state of the memory in a large computation, when I use half a terabyte of memory, which can be done with a system that's $12,000 right now, right? I need 128 seconds. That's about 2 minutes. I want it to replicate every 1 minute, and I need 2 minutes to replicate. If you replicate often enough, you don't do any computation, you just replicate. Do you see how disastrous this potentially is? You can't afford 2 minutes of replication, right? In general, even if you do it every once an hour, it's going to hurt. It's going to hurt your bottom line. It's going to be problematic. Not to mention that because the replication process is so long, any issue happening while you replicate has to be taken into consideration and could be problematic in itself, right? So in databases, for example, people talk about failure during recovery or failure during checkpointing, right? Who says you can't? I mean, in 2 minutes, a lot of things can happen, right? What happens if you die in the 2 minutes in which you were dumping the state? Well, at least you have to throw away everything you were doing because you're not sure where you died, right? It's very hard to say where were you. You see, even the information where were you, it's very hard to capture and propagate fast enough, right? So because these processors move so fast, capturing very fine-grained information about what is it they are doing at any given moment of time, it's itself a tremendously hard problem, right? That is reflected to some extent into this thing. So it's a matter of relative speed of various pieces, right? If things move too fast, you have no chance to maintain any kind of very, very tight replication. So in general, it's going to be easy to define a very nice, convenient kind of replication. But for the most part, you might not get anything close to that. With consistency, it's even worse than that. Okay? So for example, some ideas you might actually apply in here might be, you know what, I know the state is very large and so on, but maybe if I keep track of sequences of actions, very, very high-level actions that led to the changes in the state, if I can play back those actions, so I might dump all the state, but very rarely, maybe once a day, and then try to play back all the things I was doing in the meantime in order to recover. Now, that's going to have a good effect and a bad effect. The good effect is going to significantly reduce the amount of information I need to capture in the replica. The bad effect is I might take a long time to replicate. I mean, to recover from the replica, okay? This problem, for example, it's also similar to a related issue with respect to redundancy in hardware for storage. How many people know about RAID? To some extent, RAID, it's about replicas and about recovery. This replication, it's related to recovery, at least at some aspects of it. So if everything goes fine, right, in a RAID system, things get replicated in a funny way. I mean, it depends on which RAID you use. I mean, they might be mirrored. They might actually use checksums and whatnot, right? And it runs fast as long as nothing wrong happened. When something wrong happens, it might actually take you an enormous amount of time to recover from the something wrong. For example, if a hard drive fails, you can plug in another hard drive and recover the RAID array. It might easily take a couple of hours to do so, right? So a big consideration with respect to replication is look at the reason you're replicating and figure out how much do you care about the speed at which you can recover from the replica. So if you replicate for the purpose of conserving the information one way or another, you have to ask yourself the question, what's the price? For example, a very nice way to do, for example, backups, right? So usually the backups, the daily backups go on some reasonably fast storage, then the monthly backups go on some further away storage, and we also have yearly backups and decade backups on some sort of tapes that are somewhere. It easily can take you months to recover from certain backups, right? So the fact that you have a replica doesn't mean you're going to get it anytime soon, okay? That in itself is a problem. And you see, we say months, and that sounds horrible, but for the financial guys, 10 milliseconds is horrible. So if you do some replication and it takes you 10 milliseconds to get to the replication, you lost the game because the other guys are in front of you and they make money and you don't. Right? On the Wall Street now with the fast trading, because all of them use the same kind of algorithms and the same kind of things, right? It's kind of going around. If you're late to the game, you lose money. It's not so much that you don't make money. You literally lose money. And in the end, it's a zero-sum game, right? If somebody makes money, somebody has to lose money. I mean, kind of the trend is things are going upwards, but you have enough of this fluctuation, right? So always speed at which things can be accessed or replicated or recovered from a replica have to be put in the context of the specific application, right? Months to recover might be nothing if things don't happen faster than at the level of a year, for example, right? So it's all relative and all has to be considered. So the overall picture I'm trying to paint is the following. When it comes to replication and consistency, it's worth taking the time to really define what you care about and what you don't care about, much more so than the other issues. If you do so, you could pick a better compromise with respect to what's the specific replication technique you're going to use for your specific application. And I'm giving this example over and over and over again, but I think to a large extent, Amazon is the master of picking the right compromise for the replication. I mentioned this before, right? They don't even bother that much with keeping track of, for them, right? If somebody buys an item in let's say on the East Coast, it goes to a different server than somebody buying the item on the West Coast, even though it looks like Amazon.com to all of them. Instead of freaking out and saying you can't possibly sell the same item to both guys, that has a significant constraint on the replication. That means if somebody buys it here, the database server or whatever server keeps track of the transaction, they have their own database-like technology, right, would have immediately to contact all the other servers and tell them this person bought the item. Instead of doing that, they say, yeah, whatever. Why can't they do that, right? They've done this judgment and say, it's not that big of a problem to sell items you don't have. It's a much bigger problem to make sure. So for example, if you would buy an item and it will take about 10 seconds for the system to come back and say, yes, indeed, the item is yours. Most people would abandon the service, right? The uncertainty whether your purchase went through or didn't go through, it's really alienating for people. The worst of the worst was the Facebook incident on the NASDAQ. By the way, Twitter decided not to go with NASDAQ, probably for the same reason, right? I don't know if you've heard the news. They decided to list on New York Stock Exchange. They hope they have better servers, maybe, okay? So the uncertainty that something happened or didn't happen is really devastating for the humans. Now, here's an interesting question. Look, computer science is not about humans. Why is this guy talking about humans? Because ultimately, that's what determines the failure or the massive success of anything you do, right? A sure way to have a disaster on your hands is to ignore the user and to say, hey, what's a second in a person's life? Everybody can wait for a second. No, no, no. I mean, if users got used to faster things, and right, it's the difference between smooth. People say, oh, I like Amazon better because it's smooth. What's smooth? Well, that 30 milliseconds, right? Or, oh, I really hate this service because it keeps on being choppy. And a lot of services died. I mean, a lot of e-commerce sites died because they really insisted on the wrong kind of consistency, right? So these decisions, even though they look like, yeah, whatever, it's just a decision, no, it's not. I mean, it's the difference between a big fortune and complete financial ruin, okay? And it's hard as a programmer to tell what will irritate the users. Okay, let me give an example. It's not quite related to this, but it gives you an idea how much money you could lose for little things, right, in about 1 minute. Because, okay, it's too short for a replication story. So a big success story of SAS, the big data mining / statistical software that they have on their website, is that they helped Expedia make about $30 million more a year by just noticing something. So what they notice is the following. So the question is, how do you find this? Well, that's a different story. They notice that Expedia loses something like a large percentage, about 10, 15, 20% of the people through the checkout process. So they notice people find the plane they want to, plane ticket they want to purchase, they go, and at some point they abandon things. right? And the question was, why do they abandon things? I mean, nobody noticed they abandoned things. Nobody cared. It's like, hey, they only looked at how many plane tickets they sell. Yeah, everything is fine. SAS comes along, does some massive data analysis. Hey, guys, 20% of the people abandon the checkout process. So it turns out that people were abandoning the checkout process because of a single line in the page, right? So when asked to plug in the credit card information, the line there said address, credit card address. And a lot of people were confused what credit card address means. Is it the address of the bank that issued the credit card, or is my address? And they abandoned this and they went to Orbitz. They fixed this little thing. I mean, literally all you have to do is say the credit card of the card holder instead of credit card address. So the lesson here is when you're doing this kind of interfaces, especially when real humans use your stuff, try to consult with somebody who understands humans and say, does this make sense? Because you could ruin your company, right? Or make SAS rich, but they discovered that they need to improve the English in one of the sentences, right? So everything matters. Just remember that, okay? I'll see you next time when we talk in earnest about consistency and replication.